Today we will do continuity and differentiability. First of all, let's discuss continuity. If there is a function fx such that the right hand limit at the point x equal to a is equal to the left hand limit at x equal to a is equal to fa. Suppose the right hand limit at x equal to a is equal to left hand limit at x equal to a equal to fa, then we say that fx is continuous at x equal to a. For example, in type 2 of the sheet, there is a question fx is equal to x to the power 4 where x square is greater than 1 and fx equal to x where x is less than equal to 1. X square is less than equal to 1. You have to discuss the continuity at x equal to plus 1 and minus 1. That is the question. So first thing you have to do is you have to write the sum in a slightly different manner. So you will have to rewrite the sum like this: fx equal to x to the power 4 when x is less than minus 1, fx equal to x when x is between minus 1 and plus 1, and fx equal to x to the power 4 when x is greater than equal to 1. After this, you examine the continuity at the point 1. So the left hand limit at the point 1 will be equal to 1. The right hand limit will also be 1 and f1 will also be 1. So the left hand limit will be 1, right hand limit will be 1 and f1 is also equal to 1. So this clearly shows that the function fx is continuous at x equal to 1. Now let us examine the point minus 1. The left hand limit at minus 1 is equal to 1. The right hand limit at minus 1 is equal to minus 1 and f minus 1 is also minus 1. So you can see that it is not continuous at x equal to minus 1. So in this particular question, which is type 2 of the sheet, we can clearly see that the function is continuous at x equal to 1 and discontinuous at x equal to minus 1. Now let's talk about differentiability. If the limit of x tends to a plus fx minus fa by x minus a, if this is equal to the limit of x tends to a minus fx minus fa by x minus a, so we call this one the right hand derivative and this one the left hand derivative. So the right hand and left hand derivative both are equal, and they should be equal to a finite number. So if the right hand derivative is equal to the left hand derivative is equal to finite number, then we say that fx is differentiable at x equal to a. Now in the theory sheet, let us have a look at type 6 of the theory sheet. In type 6, it is given fx equal to x upon 1 plus e to the power 1 by x when x is not 0, and it is equal to 0 when x is equal to 0. You have to examine the differentiability of this function at x equal to 0. That is the question. So first we take the right hand derivative. So when you are taking the right hand derivative, this is the expression. Now if x tends to 0 plus, then e to the power 1 by x will tend to e to the power infinity. So the answer will be 0. Now let us check the left hand derivative. Now in case of left hand derivative, when x tends to 0 from the negative side, e to the power 1 by x will tend to e to the power minus infinity. So the answer will be 1. So you can see that the left hand derivative is 1, right hand derivative is 0. They are not the same. Therefore fx is not differentiable at x equal to 0. Now there is an important thing that has to be understood, that in this particular sum the function has been defined in a piecewise manner. So this is the first part, this is the second part. Because the function has been defined in a piecewise manner, that is the reason why we are checking right hand and left hand derivative. Otherwise, if you look at the question in type 7, it's given that there is a function y equal to modulus of cos x minus sin x. So the question is that you have to find dy by dx at pi by 4. So what you can do is that since this is not a piecewise function, you can do the derivative by ordinary differentiation d by dx. So for the right hand limit, it will become, the function will become sin x minus cos x. So the answer will be cos x plus sin x. So that is cos 45 plus sin 45. So that is equal to root 2. And if the x tends to pi by 4 from the negative side, then this is the function value, and if you put pi by 4, then it is coming to minus root 2. So you can see that the right hand derivative is root 2, left hand derivative is minus root 2. They are unequal, and therefore it is not differentiable at pi by 4. So if it is not a piecewise function, then you can also proceed by ordinary differentiation. Now let's have a look at the type 3 of this sheet. In type 3, it is given fx equal to x minus modulus of x minus x square. So, and it has been mentioned that x lies between minus 1 and plus 1. You have to discuss the continuity of this particular function. Now here, what we can do is that we can split this into intervals. We can split the function into interval minus 1 to 0 and 0 to 1. So if the interval is minus 1 to 0, then it will be x plus x minus x square, which is 2x minus x square, and if it is 0 to 1, then it will be simply equal to x square. Now you will realize one thing, that 2x minus x square and also x square, they are both parabola, and when you plot the two parabolas, this is the figure that you will get. You can clearly see that from one end of the interval minus 1 to the other end plus 1, all throughout the graph is positive. So that means this function is continuous in the domain. Have a look at type 4 of the sheet. In type 4, this is the function. Now you will have to examine the continuity of this function. So what we can do is we can split it into intervals. Incidentally, you have to examine the continuity at x equal to 1. So you split it into intervals. First is that suppose x is between 0 and 1. Suppose x is between 0 and 1. In that case, x to the power 2n will be negligibly small. So fx will become log x plus 2. Secondly, suppose x is equal to 1. Then the function will become like this. Thirdly, suppose x is greater than 1, then this is what you will get. So you will get minus sin x. So you have got the piecewise definition of the function. Now suppose if you do left hand limit at 1, so the answer is log 3. Suppose you do right hand limit at 1, so the answer is minus sin 1. So you can see that it is not continuous at x equal to 1. So in this manner we can do the questions of type 4. Have a look at type 5. Now type 5, this topic is called functional equations. So f of x plus y is fx into fy. So if you are trying to find the right hand limit at x equal to 0, so let us take a small positive constant h. So we can write limit of fx like this. So that is equal to limit of h tends to 0, fx into fh. So limit h tends to 0, fx into 1 plus gh into capital GH. And clearly this is equal to fx. So you can see that the right hand limit will be this. Now suppose you want to do the left hand limit. So this is what you will get. And therefore this is equal to fx. So you can see that the right hand limit and the left hand limit both are equal, and therefore it's very clear that the function is continuous everywhere. Now have a look at type 8. In type 8, one function has been described like this. One function has been described like this. So in this particular type 8, we can say that suppose if we break the question into intervals, so x is between -1 and 0, then this is the function. X is between 0 to 1, this is the function. If x is between 1 and 2, this is the function. Between 2 and 3, this is the function. And at x equal to 3, this is the function. So you can clearly see that this is minus x, this is 1 minus x, this is x plus 1, and this is x plus 2. So if you try to graph this particular function, then the graph will look like this. So this is how the graph will look. Between -1 to 0, the graph is minus x. Between 0 to 1, the graph is 1 minus x. Between 1 to 2, the graph is x. Between 2 to 3, the graph is x plus 1. And at 3, the graph is just one particular point, that is 3 plus 2. So the question is, you have to examine the differentiability. So it is not differentiable at x equal to 0, 1, 2, 3. It is not differentiable at these points. So this is known as graphical method of checking the differentiability. Now we'll have a look at type 9, which is also called the chart method. In type 9, there is a question given. So we will have to convert the data into a chart like this. So we will have to convert the data into a chart. Now you need to find f of fx. So you can see that 1 plus x lies between 1 and 2. So f of fx will be x plus 2. You can see that 1 plus x lies between 2 and 3. So that is 2 minus x. Then 3 minus x between 0 to 1. So the graph will be 4 minus x. Once you have found the values in the chart, you just need to plot a graph. And this is how the graph will look. These are the three values of f of x. So the question is saying discuss the points of discontinuity and non-differentiable. So you'll have to say discontinuous and non-differentiable at x equal to 1 comma 2. So this is how we can do the sums of the various types given in this particular sheet. The other thing is you have to remember in this particular chapter that if a function is differentiable, it is necessarily continuous, but if a function is continuous, it may or may not be differentiable. Certain functions, like any polynomial, then sine function, cos function, e to the power x, they are always continuous and always differentiable. Log x is continuous and differentiable, but only from 0 to infinity. Then tan x and sec x are continuous and differentiable everywhere except odd multiples of 90. Cot x and cosec x are differentiable everywhere except multiples of 180. Then modulus x minus a is continuous everywhere, but it is not differentiable at x equal to a. It is, in fact, the graph of modulus x minus a will look like this. So you can see that it is continuous everywhere but not differentiable at x equal to a. Greatest integer function is continuous and differentiable everywhere except integer values of x. Whenever x has an integer value, then it is discontinuous and non-differentiable. If you have two continuous and differentiable functions f and phi, then a linear combination of f and phi will also be continuous and differentiable, and similarly product of f into phi will also be continuous and differentiable. Suppose you have a continuous function f but a discontinuous function phi, then both of these will be discontinuous and non-differentiable. So if f and phi are both continuous and differentiable, both of these will be continuous and differentiable. And if one of them is continuous and differentiable and the other is not, then this one will be also discontinuous and differentiable, and same for this one. And in type 1 of the sheet, we have questions like this: evaluate limit h tends to 0, modulus of -1 plus h minus -1 by h. So you can just remove the modulus. So the answer will be -1. So this is the way to do the questions of type 1. So that brings us to an end of this particular session of continuity and differentiability.